recording. So it's a pleasure to have our very own Andrey Shkerin here with us. He just joined us for a postdoc. He'll be talking about inflation and dark matter production in Einstein-Cartan gravity. So please take it away, Andrey.
Okay, thanks for the opportunity to open the season. So yeah, I will report on recent progress done in collaboration with Misha Shaposhnikov and also Inar Timiryazov and Sebastian Zell, his students. And he has some papers on which I base my talk. And okay, so here's the plan. So first, I'll give some brief review of what Einstein-Cartan gravity is and what motivation is behind studying it. And then I'll discuss two particular applications of Einstein-Cartan theory to inflation and dark matter production. And these are two separate parts of the story, but they're kind of related to each other because they can be treated within the same framework, within the same theory. So it's interesting to study how they connect. And yeah, finally, I'll give an outlook because that's actually investigation in progress and there are many things that remain to be done here. So let's discuss Einstein-Cartan gravity. First, some general things. Okay, we know that general relativity is a successful theory describing gravity at everyday energy scales. However, we'll also know that it cannot be a complete theory. Something must happen at energy scales of the order of the Planck mass. And therefore, it makes sense to explore different alternatives to general relativity. One way to suggest something alternative is to change underlying assumptions in the theory. And general relativity is a geometric theory. So gravitational degrees of freedom, they are carried by the metric field. Apart from that, there is another geometric object, which is called the connection. And in general relativity, the connection is not independent. It is a function of the metric field. And this is kind of an underlying assumption of GR, and it makes sense to ask the question of what if we treat metric and connection as independent variables, not necessarily independent degrees of freedom, but independent variables. And in this way, we come to the so-called first order or Palatini formulation of gravity. And in the Palatini formulation of gravity, so connection is treated as an independent variable. However, it's still taken to be symmetric in the lower indices. And then, okay, so a priori, there is no relation between metric and connection anymore. So connection is not given by the Levi-Civita symbols as in GR. Instead, if we treat them as independent variables, we can apply variational principle to both G mu and gamma mu rho, and just try to obtain the relation between the metric and connection dynamically as an equation of motion. And this is indeed what we get when we vary the standard Einstein-Gilbert action with respect to the metric. We get the Einstein equations, and then we vary with respect to the symmetric connection, we get the metric compatibility condition. So therefore, the Palatini formulation of gravity, at least with this Einstein-Hilbert Lagrangian, is equivalent, classically equivalent to the usual general relativity. Now, one can make a step further and actually to drop the assumption about the connection being symmetric in lower indices. In this way, one introduces torsion. And this is kind of natural step because, as we'll see later, torsion arises whenever you have, in this framework, torsion is inevitable whenever you have fermions. And this is the Einstein-Cartan framework. So this is Einstein-Cartan theory. We have the metric field and the connection field, they are taken to be independent, and the connection is taken to be metric compatible. So we bring back this condition of metric compatibility, but otherwise arbitrary. So in particular, it need not be symmetric, and therefore the torsion is allowed. And the question of whether this torsion is dynamical or not is that's a different question. So, and in what follows in the theory in which we consider, the torsion is not dynamical. So there are no propagating degrees of freedom associated with it. And okay, so instead of metric and connection, one can work in terms of geometric objects such as tetrad and spin connection, Lorentz connection. It's sometimes more convenient to work in terms of the subjects, but I will stick to the component notation. So G mu and gamma. So now, once we have this Einstein-Cartan framework, it's natural to ask what's the real difference between the two theories from the physical point of view. And the answer depends on what theory we consider, what Lagrangian. And okay, as I said already, without if you consider just the Einstein-Hilbert term without anything else, then this is essentially the Palatini formulation of gravity, and then the two theories are equivalent. Because now you can vary with respect to the metric, you can vary with respect to the torsionful part of the connection, and then you get that the torsion vanishes dynamically. So here it's the same as general relativity. However, we can add something else. For example, let's consider the scalar field. The usual scalar field, which couples to the metric, and there can be some potential for it. Then it is again equivalent to the metric formulation of gravity, simply because there is no direct coupling to the connection of the scalar field. Okay, let's move forward and let's include this term. So this is non-minimal coupling of the scalar field to gravity. So psi is non-minimal coupling. So when we include this term, the equivalence is broken. And one way to understand this is to see that, okay, so the structure of these two terms, it is like the Ricci scalar multiplied by some coefficient, but the coefficient is still dependent. So remember, in the Palatini formulation of gravity, when we vary with respect to the connection, we obtain the metric compatibility condition, which is essentially the condition that the covariant derivative, the metric, equals 0. And there is this coefficient, the Planck mass, which is just the coefficient, so we can bring it out of the covariant derivative. But when we have this non-minimal coupling, this is no longer the case. So we no longer have the same condition. And therefore, the theory is no longer equivalent. Another way to understand why this non-minimal coupling breaks.
This is also, I mean, you can't do a Weyl transformation to.
Yeah, that's what I was going to say.
Oh, you're going to say.
That's actually simpler to understand, yeah, because in what follows, I will work in the Einstein frame, because then it's more clear what's going on.
Because what I was thinking, you know, if you ignore the last term and you say the first two terms are equivalent, adding the third term, I can go back now to the Einstein frame, and then it looks like everything is equivalent again.
Yeah, but here there is subtlety. So indeed, let's make this Weyl transformation of the metric. But here there is difference between Palatini and Einstein-Cartan and the metric formulations, because in the metric formulations, the Ricci tensor depends on the metric, so it's a function of the metric field, because there is nothing else. In the Palatini formulation or in the Einstein-Cartan formulation, the Ricci tensor is a function of the connection field. There is no metric there. Therefore, the Weyl transformation will give you different results. And when you go from the Jordan frame, so the Jordan frame is a frame, by definition, it is a frame in which there is this non-minimal coupling. And yeah, one can show that you can get rid of this non-minimal coupling by performing a certain transformation of the metric field. And then you will get the theory in which the gravitational sector is a standard one, just the Einstein-Hilbert term, but at the expense of some complicated structure of the scalar sector. say, complicated kinetic term for the scalar field, or if you introduce a canonical degree of freedom, there will be complicated potential. But the Weyl transformation depends, I mean, the result depends on whether the Ricci tensor is considered as a function of the metric or connection. And this is what brings this non-equivalence between the two formulations. So yeah, that's an important point. And what else? What else can we have here? Well, we can have fermions. As I said, fermions, whenever I rise fermions, it's natural, and in fact, it is inevitable to promote the Palatini formulation of gravity where the connection is symmetric to the Einstein-Cartan formulation, simply because the antisymmetric part of the Lorentz connection enters the covariant derivative of the fermion field. So in this sense, fermions source torsion. So Einstein-Cartan framework is a consistent framework for treating fermions in a curved space-time distortion. Since we have direct coupling to the torsionful part of the connection here, of course, the equivalence is broken.
Can I ask a question?
And, yeah.
So suppose that I integrate out these fermions or this scalar field, and I just think of gravity as some effective field theory. Then what is the difference between the two formulations? Is it that in one case you only have the metric to work with, and that's it? And you write down all possible invariants and organize them by
so
way? And in the other way, you have some B field or something, or what?
Yeah, from the point of view of effective field theory, of course, yeah. So there is this additional object, and you may think of it as something coming from geometric consideration, or you may think of it just some additional quantity, torsion. And then, of course, you may consider all possible, build all possible invariants, including torsion. And in this way, in general, well, you'll get some effective field theory. It will be different from general relativity simply because general relativity is one particular theory, right? And here you kind of explore all. So you will have more terms. You will have more terms.
To make sure I understand, this extra field that you're calling torsion, is it some, two-index antisymmetric tensor field? What is it? What is
well, you can decompose it. You can decompose it because in general, okay. So in my talk, the torsion is not propagating, so it's not new degree of freedom. So it is something that you can integrate out, or better to say, solve for, because there is an algebraic constraint. It's simple. There is simple algebraic constraint on torsion. So the torsion is not dynamical.
So it's some Lagrange multiplier field, basically.
Yeah, I guess you can think of this.
Okay, that's just a name. Okay.
But in general, of course, if you add all possible terms into Lagrangian, like all gravitational variants of mass dimension 2, mass dimension 4, there are so many of them, hundreds. Then, of course, but then in this general theory, the torsion is propagating.
Yes.
So then this is just a particular UV completion then of GR?
Yeah, that's hard to say. Okay, of course, we'd like to think you have some deep motivation, right? And it's tempting to think that, okay, so this Einstein-Cartan framework, and I will explain later also, but this Einstein-Cartan framework, the Einstein-Cartan gravity, it can be thought of as a just gauge theory of the Poincare group. Mm-hmm. And then it's kind of natural when you have in mind unification, like, unified treatment with the standard model fields. It's natural to think of gravity as a gauge force, right? And this is, in this way, you arrive at the same result, but the spirit is different. I mean, you take the theory, which is originally invariant under the global group, the group of global transformations, global Poincare, right? And then you promote it to the theory which is invariant under local Poincare transformations. And in this way, you get gauge fields. And these are, so in this setup, these are nothing but the tetrad field and the Lorentz connection field.
Yeah, but normally you don't have to do that, right? Because I thought the gauge invariance is to take that, you have the metric with 10 components, the gauge invariance gets you down to 2. So why would you have to have this extra gauge invariance then?
Well, no, that's kind of different approach. There are different approaches, right?
I see. Okay.
So the approach of gauge theory of gravity is like you have the original space-time, and on top of that, you have an additional structure. And this additional structure is some tangent space in which you have additional transformations, which are your Lorentz transformations, or like the full Poincare group. But this Poincare group acts in the tangent space, which is like the flat space. So you promote the isometry group of the Minkowski space to local transformations. So, and yeah, but this gives you this additional structure. This is not minimal setup, so to speak.
Okay.
Right. So apart from these fermions, we can now think of adding more terms, which simply vanish in the absence of torsion, but which may be here and which may contribute to equations of motion in the presence of torsion. So one of such terms is this one. So it's easy to see that, to show that when the torsion is absent, this is just identically zero. However, in general, it is not. And these two coefficients, alpha and beta, we'll call them non-minimal fermion couplings. And they will play an important role in what follows when I discuss dark matter production. Because, so this fermion field psi here, it's basically, it's any fermion field. So for example, it can be fermion fields of standard model, all of them. And then this will just give you...
Can't you use the chiral rotation to eliminate these fermion terms in favor of G mu dual of the theta term?
In favor of...
Well, formally, if there is no anomaly, you can always rotate by a chiral rotation. You can always rotate this psi alpha plus beta gamma 5 d psi into psi bar d psi, right? Psi bar d psi. Rotate away.
So I think this is no longer the case because of this torsion. So because of this additional structure, so you cannot do it in general.
But you can always do the transformation. What Misha is saying is probably there will be other terms that will pop out, right? Or you're saying that gamma 5 term?
If something appears instead, then yes, then I would say that it's fine. But yeah, actually.
But are you sure that there is a D there? So this is a
yes.
an unusual form, right? Because
yes.
Is this not? It's not a gamma 5 mass. It's an axial vector current, right, of some sort, or
yes, that's axial vector current precisely. So
okay.
we will see. So I will show you later what this term gives when you rewrite the theory in the when you solve for torsion. So when you solve for torsion, this gives rise to effective for fermion interaction, basically, these terms, which are precisely current interactions. So they will involve, well, in general, they involve both vector and axial current interactions. So yeah, and okay, that's fine. We may have this term, and also, yeah, we can now think of adding additional gravitational terms. And okay, so let's consider what objects of mass dimension 2 we may add.
Excuse me, one question. This new term which appeared on the right in brown color, it's not even Hermitian, right? Because extra I. Normally, ID is a Hermitian operator, right? ID is a Hermitian operator. Psi bar psi is also a Hermitian.
Oh, but there are eyes here. Sorry, yeah, maybe it's.
Yeah, so
there are eyes also here.
Yeah, it's it's no longer Hermitian. Even if you forget about beta, just you put here I alpha, it's already not Hermitian. Anti-Hermitian, in fact.
Anti-Hermitian.
Maybe it's not important, I don't know.
Well, here, yeah, you have such things. You might have parity violation, for example, and so, for example, this term, it's a parity violating, but yeah, I think that's not, at least by itself, it's not a problem.
Well, with fermions, the issue of hermeticity, for instance, some fermions cannot be continued to Euclidean space without loss of hermeticity.
Oh, that's
because you are in the Minkowski space.
That's very good. Yeah, that's very good point. Yeah, but this is a subtle point. Yeah. But okay, so let me continue with discussing what additional structures you can actually have because of the torsion. And so one additional structure is so-called Hall's term. So when you drop the requirement of symmetricity of the connection, in fact, you may add this combination, and it's not longer identically zero. And then this combination, it comes with an arbitrary parameter, priori arbitrary parameter of which I write as m Planck squared, and I introduce some additional dimensionless coupling, and this coupling is called Barbier-Emirzi parameter. And this whole thing here, without the non-minimal coupling of the scalar field, is called the Hall's term. And this is quite an interesting term. So people consider it from the point of view of theory and phenomenology also. So that's a known thing. But one can also couple it non-minimally to the scalar field in the same way as we couple Ricci scalar to the scalar field. So we get this additional term, which is non-zero in Einstein-Cartan gravity. We can also have this term. So this is a so-called Ni-Yang invariant. And one can see, again, that without the coupling to the scalar field, this is just total derivative. So it doesn't contribute to the equations of motion. However, when we couple it to the scalar field, it gives a non-trivial contribution. And yeah, so this is like a new topological invariant, which is absent, which is present in space-time distortion, which is not related to earlier or to other topological numbers, earlier Pontryagin classes. It is intrinsic for space-time distortion. Okay, and let's stop here. Of course, we may continue the series by including more terms, by including terms, for example, of quadratic and curvature, or by including terms involving derivatives of torsion, and so on. But we'll stop here because, yeah, okay, including terms, for example, of higher order in scalar curvature would complicate the analysis. Qualitatively, the results are expected to be the same, while including terms involving derivatives of torsion would give new degrees of freedom associated with torsion, and that's what we don't want. So we don't want to include to bring new degrees of freedom. So it's kind of minimal setup. And okay, as I already said, Einstein-Cartan gravity can be thought of as a gauge theory of the Poincare group, and in this sense, it is close to the standard model, framework. So it's and therefore it's natural to think of gravity as a. I mean, Einstein-Cartan framework is something which is interesting to study in this context. And okay, having in mind.
So basically, in order to do all that, you need torsion to be non-vanishing. However, let's ask a question. Okay, gravity at large distances is well studied. We know the orbits of planets very well. We know some other basically classic gravity. Let's say you add non-vanishing torsion. I mean, are there any constraints in the normal gravity, Einstein gravity, for coefficients in front of this torsion or some?
Yeah, this is model dependent. So this depends on what particular model of torsion you consider. So in our case, there are actually no such constraints because, well, again, so just let me explain. So because in our case, it's very easy to deal with torsion. You can solve for it. It's not dynamical. Okay. So, and when you solve for it, you arrive at a theory which is equivalent, at least classically equivalent, but which is now without torsion. So there is no torsion there anymore. Okay. So the torsion gives rise to additional structures. So it gives rise to operators of higher dimensions.
Okay.
Is it fair to say? Is it fair to say that since the torsion is not propagating, it's like a Lagrange multiplier? When you solve for it, you get contact terms and no longer.
Well, yeah, I didn't think of it as Lagrange multiplier, but I think it's yeah, one can think of it as Lagrange multiplier.
What dimensions get after eliminating the torsions? What dimension operators do you get?
Yeah, I will show it next slide.
Okay.
High dimensional, okay. Misha. It will be point-like interactions, I think.
Well, in fact, yeah. So there will be, for example, there will be this current fermion current interactions, which are 6 dimensionals, which are suppressed by m Planck squared. So unobservable in experiment, but as we will see, they can produce dark matter efficient. These interactions. Okay, so having in mind this phenomenological applications of this framework, we will associate phi, so the scalar field, with the Higgs field, degree of freedom, and psi with the standard model fermions, plus maybe some additional singlet fermions, Dirac or Majorana. Okay, and then the Higgs gives rise to Higgs inflation, and this fermions gives rise to dark matter, fermion dark matter production. And yeah, for the potential, it's so let's take it just to be the quartic potential, as for the Higgs field. Okay, and here comes the most important question: what's the difference of this theory with torsion as compared to the theory without torsion? And to answer this question, one can actually eliminate the torsion completely. So here it's not propagating, so we can just solve for it. And in fact, the theory is simple enough so that we can solve for it explicitly. So the equation of motion for torsion reduces just to a linear algebraic constraint. So we can find the solution, plug it back into the action, and in this way we arrive at a sort of effective theory. But this time it is now in the metric formulation of gravity. So we arrived at an effective metric theory. And so this is how it looks like. Yeah, so one step would be to solve for torsion, and another step would be to make the Weyl transformation of the metric to get rid of the non-minimal coupling of the scalar field to curvature. So
you're saying now that, sorry, so you're saying now that the couplings of the kinetic term for the gauge field is now fixed once you've solved for the torsion. Is that the idea here, right?
These are fixed, yes. Well, the whole idea, yeah, I think the idea here may be the following: that, okay, so you obtain the theory where now there is no torsion, and you may notice that, okay, so there is this action which involves the usual gravitational term, then there is a scalar sector with a non-canonical kinetic term, but this in turn you can make it canonical by redefining the field phi. And so there is a fermion sector where now the covariant derivative doesn't involve torsion. And now there are additional terms, which are high dimensional terms. And this is what we get from torsion. So we get a particular subset of high dimensional operators.
I see, and because I could just add these terms by hand anyway, right?
Yes, yes. Precisely. You can add them by hand, but here's a specific subset of them, and I will argue that this is a very interesting subset.
Oh, okay. Okay, great.
And yeah, so here there are like three contributions. There is a scalar part. So it involves interactions of the scalar field with itself. So this eta and gamma, they're basically the functions of the scalar field. And this will be important in the context of inflation. And there is also the scalar fermion interaction, which may be important for dark matter production. And there is also the four fermion interaction. And yeah, in the part dedicated to dark matter production, I will mostly discuss the four fermion interaction for simplicity. Yeah, so here we see that the torsion leads to appearance of this contact interaction terms, axial vector, vector, and axial interaction. And we also see that this interaction is suppressed very much by Planck. So I would say that yeah, we will see what this implies for dark matter production.
It's not even M Planck squared, because comparing to the leading term, which is proportional to M Planck squared, this term is 1 over M Planck squared, right? So 4 powers of M Planck.
Yeah. So naively, it's very much suppressed.
Yeah.
So naively, you wouldn't expect it to do anything.
Yeah.
However, I mean, so yeah, one should have in mind that this is still okay. This is a gravitational interaction. So I will discuss dark matter production. Dark matter can be.
Yeah, but this is a dimension 6 term that you would normally add to any Lagrangian. It's suppressed by 1 over m squared.
Misha, Tony, sometimes this in this gravitational literature, the normalizations of fields are slightly funny, right? So we usually normalize derivative of the boson field squared being dimensionless, right? But in the gravitational literature, they put M Planck in front, M Planck squared in front. So one has to be apprehensive of that. Yeah.
No, but I think but isn't the 4 fermion interaction that's normalized correctly, right? It's dimension 6.
I think so. Yeah.
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 Yes. Yes. Well, just a general remark. Okay, one may expect this to be too much suppressed. However, it is. I mean, gravity is strong enough to produce dark matter. I mean, gravitational production of dark matter, it's okay. It is there. It's strong enough to produce necessary abundance, even overproduce oil. I will maybe tell more about this later. But yeah, anyway, so this is what we have. This is what theory. This is our theory, and yeah, let's now study 2 applications. So first, let's study how inflation goes in the theory. And for this part of the talk, I will need, okay, so this scalar part of the action, including gravity, and also this scalar self-interaction part. Okay, so what's the story here? So yeah, and if we associate the scalar field phi with the Higgs field, then we come to some generalization of Higgs inflation. Okay, and what's the story behind Higgs inflation? Let me explain briefly. So yeah, it is exciting to think that Higgs boson can be the inflaton field, and well, but that's not possible just in the minimal setup, just a standard model plus gravity. So for this to become possible, you should introduce non-minimal coupling of the Higgs field to gravity in this way. And so that was actually our motivation, our main motivation to introduce a non-minimal coupling back in Einstein-Cartan theory to study how inflation, how this may be relevant for inflation. And this proposal of Higgs inflation, it is interesting because it doesn't require new degrees of freedom beyond those of the standard model and general relativity. So now
can I ask a question here though, because from what I remember of Higgs inflation, but I could be wrong, is that the psi there was a very large parameter, and so there was questions with quantum corrections. Is that still an issue?
Yes. Well, it is not an issue. I think it is quite well understood now.
Okay.
In what sense there could be issues with quantum corrections, in what sense there are no issues with quantum corrections. So indeed, in the original proposal, in the metric formulation of gravity, Higgs inflation, psi must be of the order of thousands, several thousands, to account for, I mean, to get predictions compatible with observations. And then, of course, it's natural to ask, okay, so there is such big values, will they destroy everything, will they destroy inflation and so on? And one may even ask the following question. So yeah, I will come to the second part, but I think it's okay. So in this Higgs inflation, okay, people started thinking about cutoff, for example, of the theory, right? So you have the theory of the scalar field. Let's disregard for the moment the rest of the standard model. So you have the scalar field, you have gravity, and you have this non-minimal coupling. What's the cutoff of the theory? And well, it was computed to be en Planck over psi, the vacuum cutoff. And this is actually lower than the characteristic scale of inflation, right? And however, by itself, this is not, this doesn't mean that the theory is inconsistent, simply because during inflation, this high inflationary background, this is a classical background. So when you study quantum corrections, or like you study cutoff by considering perturbations, you should consider perturbations on top of that classical background to answer the question whether this classical solution is okay or not, whether this classical approximation can be applicable. And so the cutoff is field dependent. So it depends on the value of the background on top of which you compute, on top of which you consider compute scattering amplitudes and so on. And then one can show that this background dependent cutoff, it is in fact always higher than the scale of inflation. So in this sense, inflation is consistent. Another question is about, of course, inflation is consistent, and the predictions, I mean, the inflationary observables, it is robust in this sense, but it is not robust in the following sense. The fact is still that the vacuum cutoff is lower than the scale of inflation. And this means that in general, you cannot relate low energy observables, you cannot continue them to the high energy scales, to the scales of inflation, and to relate them to inflationary observables. So you cannot say what's the value of top quark Yukawa coupling, for example, those scales, because there is a breaking here. So there is a cutoff scale which is lower than the scale of inflation. So you lose connection between low energy and high energy observables.
But so then this cutoff is dependent on the value of the inflaton as it's rolling, right? So
yes.
You assume M Planck values for this, and
yes. I mean, yeah, during inflation, the scalar field takes high values, but okay, the Hubble rate basically what gives you like the characteristic energy scale of inflation is given by the Hubble rate, and it is lower than the cutoff.
But the cutoff is higher than the usual cutoff, provided that the value of the inflaton is around M Planck. Is that?
Yes. Well,
because if you make it smaller than M Planck, the cutoff would be okay. But if you make it larger than M Planck, then you would start to invert the cutoffs.
Well, there are different regimes, but the general story is that, yeah, when you rise the value of the scalar field, the cutoff rises accordingly. And also, although the inflationary value is above the cutoff, but it is above the vacuum cutoff, but it is always below the field dependent cutoff.
Oh, okay. So it's always below. Okay. Yeah. Thanks.
Yes. Okay, so this is the original Higgs inflation, and it was studied intensively in the metric formulation of gravity. And then almost immediately after, after the original proposal, it was also studied in the Palatini formulation of gravity. And as I said above, the two theories are not equivalent as long as you have the non-minimal coupling of the scalar field of gravity. So that's why Higgs inflation is sensitive. So in the sense, it is sensitive to the formulation of gravity that you use. So metric inflation and Palatini Higgs inflation, they give different predictions. Well, okay, so just to for consistency, I should say that yeah, there are also studies in more exotic contexts, in more exotic gravitational theories, such as teleparallel theory of gravity, where you say that the curvature is zero, but the torsion is not zero, or even in the affine formulation of gravity, where you don't introduce symmetric field at all, and you only fundamental variable the connection field. But okay, so this I will not consider this exotic options. And yeah, it makes sense to say a bit more about Palatini Higgs inflation, just a few words, simply because, as I said, Palatini naturally extends to Einstein-Cartan once you include fermions. So that will be that is interesting for us. And again, this is what gives us motivation to study Einstein-Cartan, because in certain sense, Palatini Higgs inflation is advantageous over the metric inflation. And one reason I just explained, in the metric inflation, you have the vacuum cutoff is lower than the characteristic scale of inflation, and therefore you lose, or like there is no connection between low energy observables that you can measure at collider experiments, for example, and high energy inflationary observables. However, in Palatini Higgs inflation, the vacuum cutoff is higher, so it's m Planck over square root of xi against m Planck over xi, and xi is a big number. So the cutoff is higher, and it is actually slightly above the scale of inflation in Palatini Higgs inflation. And therefore, this connection, or possible connection between low energy observables and high energy observables, it is more robust. So as an example, I will not explain in details, but so this is also what we studied. So for example, if you think that this connection is robust enough, that there is no new physics involved that destroy it, then, for example, you may obtain the upper bound on this non-minimal coupling from on the non-minimal coupling, which is an inflationary observable, an upper bound on xi from the lower bound on the top Yukawa coupling measured at LHC. So you may obtain this type of relations, which is very, very interesting. And also another point is that in metric Higgs inflation, because of this low vacuum cutoff, you may not have robust enough treatment of preheating, because the preheating temperature goes above the cutoff. So there is some part in the history of the universe which you cannot treat consistently in the metric formulation of Higgs inflation. It appears that in the Palatini formulation, you can treat it consistently, so the temperature is below. But this is, again, a subtle question, because the full treatment of preheating would include it's a complicated analysis on a lattice, and here the work is in progress, but estimations show that, yeah, in this sense, the Palatini Higgs inflation is also advantageous over metric Higgs inflation, and this gives us additional motivation to study Einstein-Cartan theory and Higgs inflation in Einstein-Cartan theory. So yeah, so after this general discussion, let's be a little bit more specific. So yeah, as I said, we consider the theory, this part of the theory. So there is a complicated. So basically, this is just a complicated kinetic term for the scalar field phi, and you can always make it canonical by performing certain transformation of the scalar field, and then all complications go to the potential. So in this sense, it is a usual inflation, just one field inflation, nothing special about that, just with some complicated potential, which involves many free parameters. So all these non-minimal couplings, they will be there. And okay, so far we restricted ourselves to classical analysis, and yeah, of course, it's important to study systematically quantum corrections on top of the classical inflationary background in this general theory. So that goes to the outlook. And so what can we expect from here? So this Einstein-Cartan, it is a generalization of Palatini. So it's natural to expect that the Palatini Higgs inflation and in fact the metric Higgs inflation, so both theories, they will appear as particular cases, as some limiting cases, in some corners of the parameter space of this general Einstein-Cartan Higgs inflation. And this is what indeed happens. So yeah, let's consider just one example. So here, for example, we switch off the Holst term and we only consider the Ni-Yang invariant. Okay, so we set to 0 these two couplings and we study Xi and Xi eta. So what we do here, we fix the number of if-folds to be 55. Again, the number of if-folds, we cannot know it precisely because that requires the knowledge of the full history of the universe, that requires the knowledge of the heating temperatures. We cannot know it precisely, but the estimation is that it's we can have a convincing estimate. And moreover, the results are only mildly sensitive to precise value of n, so it's okay. So we fix n, we fix normalization of the power spectrum, and then we ask ourselves at what values of parameters we get predictions compatible with observations. And we obtain this plot, just as an example. So here we plot the spectral tilt and tensor to scalar ratio for different Xi and Xi eta. And what we see here is that in this region, we reproduce the Palatini Higgs inflation. And this point here where Xi, I believe Xi equals Xi eta, we reproduce a metric Higgs inflation. It's easy to see that just by looking at the kinetic term of the scalar field. So it has some complicated structure, but you just take particular values of the parameters and you see that it reduces either to Palatini case or to metric case. So there is nothing really complicated about it. But it's interesting to note that we have these smooth interpolations between two known regimes of Higgs inflation. So we have enough parameters to interpolate between them. And it is also interesting because Palatini Higgs inflation and metric Higgs inflation have very different values of R. So the value of NS is pretty much the same. And in fact, this is like a very constant relation. So in many cases, in all this parameter space, we encounter this relation between NS and N. So NS is pretty much constant. However, the tensor to scalar ratio can vary. It can be as small as 10 to minus 10. It can be as large as 1, and therefore ruled out by observations. And in this plot, for example, we see that it varies from the values typical for the Palatini model to the values typical for the metric Higgs inflation model. And then it becomes even bigger and it becomes inconsistent with observations. So this is a very typical picture of what we get when we study inflation in this general framework. So just one more interesting example, different corner of parameter space. This time we switch off the non-minimal coupling of the scalar field to the Holst term, and we switch off the Ni-Yang term. So let's call it Holst inflation. So again, here we have different corners of the parameter space that reproduce either Palatini or metric models, and we have some interpolation between them. However, in this case, we see that okay, so not everywhere, so not everywhere this can be consistent with observation. So here, NS simply becomes too small, and in fact, the slow roll condition is violated. And this is an example of a quite general phenomenon that we encountered in our study, that it is possible that during inflation, at some brief moment of time, you have a violation of slow roll. Okay, so there is brief moment of fast roll, followed again by a more by a long period of slow roll. So there are two periods of slow roll separated by a brief moment of fast roll. And that's actually very interesting because it can produce some features. This violation of slow roll can produce some features in the power spectrum, for example, that could be potentially observables and so on. So that's There is an interest in studying such features in inflationary potentials, the recent interest. So we also find it very interesting that here we have this this feature. So basically what we have is that we have some Palatini phase of Higgs inflation followed by the metric phase of Higgs inflation, and the two phases are separated by the fast roll. And if this fast roll happens precisely at the moment which corresponds to CMB, then it's inconsistently excluded. So that's what happens.
How do
Okay, so here's.
But can I ask you again about these cutoffs? I mean, are you always assuming that your cutoff, it's what you called lambda 0, is that M Planck?
No, lambda 0 here, yeah, that's in general, we don't know. Because in general, we have so many parameters that it's impossible to discern any analytic expression. It's not difficult to compute, and whenever we could compute it, we found that it's well, it is some function. So it's M Planck divided by some function of non-minimal couplings.
Yeah, because
right?
you see, you're taking values of xi like 10 to the minus 6, and so that makes the cutoff way bigger than M Planck, right? So.
No, well, there are
it was
different
the previous
couplings.
plot. It was, you had the previous plot on the previous trend. Yeah.
Right. No, here actually, okay, so one of the parameters can be small, but another parameter is large. And actually in the cutoff, what enters in the cutoff is a combination of these two parameters, and it is always the larger one which wins. So it is below the Planck mass.
I see. So yeah, because I would say that you always have to have a Planck scale cutoff, and then if you're playing around with the cutoffs, it can only be lower, right? Because you don't want to make cutoffs higher than that.
No, I agree. Yeah, that's a good point. But yeah, whenever we can compute it analytically, we see that it's below the Planck mass.
Yeah.
And if okay, so it's important, of course, to study this in general. But if we encounter, but I don't believe that we encounter any region in which it is above the Planck mass. That would be too unusual.
Okay.
Yeah. So and this is what we have in general case. So we just add one more parameter into the model, and then our one-dimensional curves, they promote to two-dimensional surfaces, and this is just the particular plot of what we may have when we scan over all available parameter space of the theory. So different cases are possible. Again, this plot is to illustrate that often the spectral index it is constant. It is close to 1. It is more or less constant across this parameter space, while tensor to scalar ratio can vary significantly. And well, okay, so there are more plots, and I think I just skip them. So this is to show that the case xi equals 0 is included. Yeah, just one important comment is that we consider positive values of non-minimal couplings, because there is a question, of course, of positive definiteness of kinetic term. Whether you have a healthy theory, kinetic term must be positive definite, and this is always true as long as all couplings are positive, and that's a case that we consider, or non-negative. But in principle, it is possible to consider some of the couplings negative as long as this gives you healthy theory. So, and that's what was done in another work by other people also recently. So overall, we see that the Einstein-Cartan theory describes a rich and interesting set of inflationary models, and the significant part of these models is in agreement with the durational bounds. So that's the main result of our studies of inflation in Einstein-Cartan gravity. So now, yeah, I don't know, I'm running out of time, but okay, let me briefly then explain the dark matter production. So this time we're concentrated on this part of our theory, so including four fermion interactions, scalar fermion interactions, and fermion field. So what's the story here? So let's switch off, for simplicity, let's switch off the whole term and scalar field. Then what we have from Einstein-Cartan, from solving for torsion, we have this effective four fermion interaction, okay, the current-current interaction, which involves vector-axial, coaxial interactions. And it's important to note that even in the absence of non-minimal fermion couplings, alpha and beta, this for fermion interaction is there. So even in the minimal setup, torsion gives rise to for fermion interaction, which in this case is axial-axial interaction. And okay, so let's now try to see how it can work for dark matter production. So this vector and axial current, in principle, they consist of all standard model fermions, and one could add also some additional degrees of freedom. So let's just add a new singlet, which can be Dirac or Majorana. So this is our currents, and then because of this current interaction, this opens up a new channel of production of n particles in the early universe, simply due to this process. And if we worked in the original formulation of the theory with a torsion, we would insert a torsion leg here. But when we integrate it out, it reduces to this effective vertex. And the strength of the coupling is proportional to alpha squared, beta squared, that is suppressed by the Planck mass. And
excuse me, but what if I just have just a regular one graviton exchange? Is this parametrically different? Like if I have two fermions annihilating into a pair of other fermions due to a S-channel graviton exchange, but just a regular diagram, right?
yeah,
It's
I
also going to
understand.
be 1 over m Planck squared, right? What's
That's an interesting question. We'll see. That depends on the values of these couplings, alpha and beta. I will show you that the most interesting
let's put alpha and beta to 0, right? That's what I'm saying. Like, yeah, I can always have two same kind of fermions, fermion and antifermion, annihilating into an off-shell S-channel graviton and giving rise to a pair, right? So it's
not local. Maybe this is important. You see, this is a point.
Well, in the S channel, Misha, what's the difference, really, right? I mean, like they both scale as 1 over m Planck squared. That's the important part, right? All the rest is going to be similar, right? Given by the energies of particles, right?
Look, yeah, this is an interesting question. I don't know the answer. Yeah.
By the way, what is the contents of the dark matter sector? Is it built of n particles, or what it is built of, or axions, or?
Yeah. So how? Yeah. So here I'm going to argue that all dark matter can be this n particles. So this for fermion interaction can account for all dark matter.
I see. So you introduced an absolute scalar, standard model scalar. You call it either Dirac or Majorana.
Yes.
Then you say that that's our dark matter unit, right?
Yes.
Is it
yes.
heavy, this n?
That depends. That depends on the values of alpha and beta. So this is the next slide. So okay. So this is a general formula. So once we have this interaction, we can run the usual routine of computing the abundance. And this is what we get. Okay, so for the abundance of n particles due to this channel, and okay, so we normalize the mass to 10 keV. It will be clear what follows, and the temperature of production, the maximal temperature of production to m Planck, and Cf here is a coefficient which just some bilinear function of alpha and beta, which is different for Dirac or Majorana species, but the difference is not crucial. And okay, so let me just say one thing. So the main assumption behind this formula is that we assumed that the standard model fermions are thermalized. So we take Fermi-Dirac distribution function for the standard model fermions, which could not be the case, of course, because so this production temperature, it is associated with the temperature of preheating. And again, if you want to compute precisely the distribution of fermions during preheating, that's a complicated calculation. But yeah, so this is our main assumption, that fermions or standard model fermions are thermalized. These new n particles are not thermalized, and they're never thermalized because interaction is too weak. But yeah, I will show you also the momentum distribution.
Yeah, but can I just ask a question here? I mean, it's related to what Maxime asked you. I mean, I can always add a 4 Fermi interaction suppressed by 1 over m Planck squared with some arbitrary coefficient, right? So wouldn't I
Yes.
get the same abundance?
Yes, you would.
formula?
Yes, you would. Yes, yes.
So
this is
so then the point is that, I mean, so what's going to be critical here is the values of alpha and beta. Is that what's going to be important?
that's going to be important. However, I mean, even in this framework, well, I mean, the main motivation is, again, we have kind of unified framework, this Einstein-Cartan. So this is, as I said, we have not all possible high dimensional operators, but a specific subset of them. But even in this subset, alpha and beta are a priori unconstrained. They're just parameters.
I see.
But then, yeah.
So you're saying it's just more of a complete picture, because then you have this scalar field, which is playing a different role.
This is complete picture, and this also matches nicely with this discussion of unification with standard model, gauge theory framework, and so on. So that's okay. So this is a general formula. If you want to get some numbers, we should estimate this production temperature. As I said, this is just preheating temperature. And okay, we don't know exact number, but we can have some convincing estimate. And so this is this estimate. This was actually computed in the framework of Palatini Higgs inflation. But okay, so one can see that the most important part is here and Planck over square root of psi, which is the same both in metric and Palatini Higgs inflation. And you see that this is in the metric Higgs inflation, this is higher than the vacuum cutoff. So that was what I was saying earlier. And there is this factor lambda is a Higgs self-coupling, and this is a number of degrees of freedom. Yeah, sorry, I think it should not be 1 here. It should rather be 2 or something. Yeah, I think it's 2. Sorry for that. Okay, so once we have this estimation for the preheating temperature, we can compute the abundance, and in general, it is a function of this non-minimal couplings alpha and beta, of course. But let's consider 2 particular cases, which are most interesting. So the first case is just to set these 2 non-minimal couplings to 0, so the minimal setup. In this case, you can produce the necessary abundance of n particles, but this would require a rather large mass of the n fermion, so like 10 to 8 GeV. And I think this 3 stands for the Dirac fermion and 6 stands for the Majorana fermion. So interestingly, this almost hits the bound of following from the gravitational production of fermions just during the radiation domination stage, which is around 10 to the 9 GeV. But okay, still, I mean, on general grounds, it's possible to have such heavy fermions. Why not? The case which I think is more interesting is that when we take both couplings to be of the order of square root of psi, because in this case we have the same cutoff scale in all sectors of our theory, both in the scalar sector. This is a scale. This is a cutoff scale associated with inflation, and now in the fermion sector, the cutoff scale is also m Planck over square root of psi. And in this case, we can account for all dark matter as long as the mass of n is around 10 keV. And this is very interesting because, okay, so this is warm dark matter, nice, but not only that. So this keV scale dark matter, it's very interesting in the context of sterile neutrinos. So one plausible candidate for dark matter particle is sterile neutrino particle. And there, like keV scale neutrino, it fits nicely the model, like the neutrino minimal standard model developed also by Misha Shaposhnikov and others. And so this is good to have this number. And let me show you also the momentum distribution. So this is like one more piece of information that we can extract from this from studying how they're produced. And so what's shown on this plot? So here, blue line shows the momentum distribution of let's say this n fermions or sterile neutrinos produced due to this 4 fermion interaction. And yeah, so this is just distribution function, and y is a ratio of energy over temperature. for the particular mass, which is 7.1 keV, which is associated with a possible 3 keV signal. So that's so this is for this is what for fermion channel gives us. And for comparison, I plot here like the thermal distribution, the same temperature. So here we take just some temperature, 1 MeV, and we see that comparing with the thermal distribution, we have like a lower energy, a lower average momentum. So this distribution of N particles, it is somewhat colder than the thermal distribution at the same temperature. So in this sense, it is different from the thermal. And also for comparison, here there is a plot of what follows from the so-called resonant production of sterile neutrinos. So the story here is the following. So suppose you have the sterile neutrino, dark matter candidate, and the question is how it's produced in the early universe. And of course, different mechanisms are possible, and this is all model dependent. But again, in the minimal framework, where you have just say one additional sterile neutrino, or maybe 2 or 3, if you want to account also for baryon asymmetry, for example, then basically they will be produced simply because of their mixing with active neutrinos, and also because of the medium. So there are like 2 channels here. So non-resonant production, which comes from the mixing with active neutrinos, and also resonant production, which also comes from the mixing, but it is resonantly enhanced due to just this MSW effect of resonant enhancement of oscillations of neutrino in matter. So non-resonant production is basically ruled out or strongly disfavored by constraints from X-ray observations and so on, non-observations. While resonant production is still interesting, and here just for comparison, I show the plot. So this is how it looks like. So overall, we see that this for fermion interaction, it opens up a new production channel, and it gives us quite specific prediction for momentum distribution of dark matter particles, okay, which is different from other mechanisms. Okay, so let me finish. So here is just illustration that it can be very interesting in the context of a neutrino minimal standard model, for example, when you have 3 additional right-handed neutrino species, and one of them can play a role of dark matter, while 2 others can count for things like baryon, the asymmetry of the universe. And but that's what I said already. And also, so far we consider just a minimal, that's the simplest case. Of course, we can consider more general case. We can switch on the Hall's term. We can switch on all additional couplings. And okay, so switching the Hall's term, it modifies the couplings in this for fermion effective interaction. But I mean, qualitatively, the results remain the same. It's just you'll have one additional free parameter, which is Barbero-Emirzi parameter. Now, including the scalar fermion interactions, remember that we have also the scalar fermion interaction. It gives you yet another channel, right, where just scalar to NN bar, and it may dominate over the four fermion channel in certain regions of parameter space, but still, I mean, both channels, they ultimately have gravitational origin, so they due to the torsion. So in this sense, this is all gravitational production of singlet fermionic dark matter. Okay, so that was the second part. And now outlook, of course, yeah, there are many things to be done here. For example, yeah, as I said, one should continue investigation of Higgs inflation and the general Einstein-Cartan framework. the study of cutoffs, for example, and so on, and also different regimes. Next, it would be very interesting, but yeah, I think I have no time for that. But in general, it would be very interesting to consider also scale invariant alternatives, so scale invariant modifications of Einstein-Cartan gravity, where you so here we have just basically one parameter, which is M Planck. I mean, in the standard model and gravity, and in scale invariant model, you replace M Planck by vacuum expectation value of some additional scalar field, the dilaton field, and that's also that can give you very interesting inflationary models and so on. So that's interesting to study scale invariant models of Einstein-Cartan gravity. And of course, it's interesting to explore other terms in the general action of Einstein-Cartan gravity, for example, to include terms like R squared and so on, and to explore their consequences for inflation and possibly dark matter production. Okay, let me finish here. Thank you very much for attention.
Okay, thank you, Andrey.
Thanks.
You can applaud. Are there any questions?
Yeah, Andrey, I have a naive question. I'm wondering, in your results, it seems hard for me to understand what's the role played by this torsion term for your dark matter production.
Sorry, what's what?
What's the role played? Yeah, it seems to be not there in some sense. I don't know. Yeah, no.
Well, this is you can think at least in two different ways about this effective for fermion interaction, right? You may think of it as just some terms, high-dimensional terms that you add, well, simply because you can, within the effective field theory framework, right? So they're suppressed by M Planck squared, they're very weak, but they can give you dark matter. On the other hand, if you start from Einstein-Cartan gravity, then these terms appear inevitably,
right,
when you solve for torsion. And they appear, you see, with specific couplings.
Sure, but it's even there. Yeah, it's even there when I turn alpha beta goes to 0, right? And
yes, yes.
So
here, well, yeah, one can say, okay, so one can say one thing. So Einstein-Cartan, it gives you, okay, so there are two couplings here, but there are three coefficients. I mean, there are three terms and two couplings, so it gives you some subset. So that's one thing that it does. Yeah, I mean, if you study like the original theory, it's not necessary just to solve for torsion, right? You can, it can be there. You just should remember that it's not dynamical, it's not propagating. But then it would be something like this vortex with where you insert this torsion leg. So that would be the diagram. So yeah.
No, but a coupling like that is generic in say in string theory, or I mean, because you have massive Planck scale particles that can be exchanged by fermions, and so you can easily generate a dimension 6 term suppressed by M Planck. I would say it's generic at the Planck scale.
That is very generic. No, maybe this particular relations between the coefficients are not generic, but
that's right. That's not generic, but generating a 4 Fermi term, that's quite generic.
Yes.
Okay, let me ask maybe the question a different way, in a more naive way. So if I replace the standard model particle, instead of using this torsion as a source for those dark matter particles, is it the viable source for my dark matter production, or it is not?
So if you replace torsion by what?
If I replace the standard model particles in, just use torsion as the external force to source some of my dark matter particles, is that a viable process or not?
If you just replace it by some external source.
Yeah, I saw the torsion is can be viewed as the source of particle production. Maybe I'm too naive.
Well, no, it is source term in the sense that In a sense, I mean, yeah, maybe I just didn't understand the question, but as far as I understood it, the statement is that spin source torsion. So, and therefore, whenever you have fermions, mass and gravity, you have torsion. So you cannot get rid of it. It's always it is there. But as we said, yeah, this interaction is in general quite generic, and of course, solving for torsion is only one way to come to it. You can just add it on general grounds. There is nothing wrong in that.
Thanks.
So I had a question. Did you check that, for example, I know that in the new MSM, they have all these specific predictions to explain neutrino mixing plus dark matter. So I guess with the inclusion of this production mechanism, you kind of decouple some of the dark matter specific parameters. Has that analysis been done to kind of understand whether the model becomes more flexible or?
Some of it been done, and okay, so I don't think that we have full answer. However, yes, of course, I mean, the constraints are relaxed. The constraints are relaxed because you have this additional channel. And in particular, I mean, for example, okay, so there are constraints.
So let me ask in another way, the mixing of your dark matter fermion, which is like 10 keV, for example, that neutrino mixing could be arbitrarily small as far as
it could be arbitrarily small. It could be even set to 0. But if it's set to 0, then you don't have conventional channels of production like resonant, non-resonant. However, when you add this for fermion interaction, you can still produce N1 simply because of due to gravity. So in this sense, it is more flexible.
So then I guess it would be just any other singlet fermion that doesn't mix with neutrinos. And there's another, some people have discussed this in the literature where you have a several keV stereo that also has some 4 Fermi interaction with the standard model plasma, and you get some resonances in the matter effect of that state. Is this relevant for you? Or
I vaguely remember, but I'm afraid that, yeah, I can't comment on that. I vaguely remember some papers on that.
It may be that your strength is just too weak.
At least one paper. Yeah, I vaguely remember one paper. No, I don't want to say that there are mistakes there and so on, but okay, I didn't like it for some reason.
Okay.
and then I just forgot about it. But yeah.
Okay.
I have a question that's kind of orthogonal to all of this. So I know that Einstein gravity is fairly easy to embed in string theory. Like, you know, quickly get Einstein gravity from string theories in a fairly straightforward way, modulo the fact that we don't really know how to get the standard model necessarily, or maybe you would worry that we don't know. But if you just want to get something with Einstein gravity in it, that's easy. Can Einstein-Cartan gravity be embedded in string theory? Or are there some solutions to it? Do you know? Has anybody tried this?
No, as far as I know. You see, I can say a few things. So as far as I know, it's not so interpret torsion in the context of string theory, right? So there may be some, I don't know, problems or something, but it's not completely trivial. Okay.
Isn't that what the NS-NS2 form give you?
Yeah, no, you normally do have torsion in string theory. It's just,
exactly.
It's just
you do have.
It's the dual of the axion dilaton, you know, the axion part of the dilaton. If I'm
okay, then okay. The honest answer will be that I don't know how to. I don't know any literature. I can only say that. So this Einstein-Cartan and this modifications of gravitational Lagrangian by including the whole term, for example, they are mostly studied. I mean, from the point of view of theory, they're interesting in the context of canonical quantization of gravity. So there it is important because there it is important from which classical Lagrangian you start, how you choose your variables, which variables to quantize. So there it is important, and therefore, mostly people from canonical program, they study this, having in mind canonical now.
The reason that I ask is, as you know, there's been quite a lot of work recently on trying to understand which effective field theories really make sense if you quantize gravity, regardless of what assumptions you make about how you do this. Right, so
Yes.
this is a swampland program, but the bottom-up version of it, not the one where you're trying to derive things from string theory.
Yeah.
But at least if you derive things from string theory, you're fairly well guaranteed that it is embeddable in quantum gravity consistently. And many things that you would try to write down, the generalized GR, would run into problems. So it's not a priori obvious to me that what happens to Einstein-Cartan gravity from this point of view. And so that's why I was asking the question to try to guess whether it's in the
well, again, so here it's quite harmless because again you can solve for torsion, you can write an equivalent metric theory, and there it is just like normal gravity plus some extra high dimensional terms that would be there, right? And it is just particular relations.
They can be arbitrarily small, those higher dimensional terms. The coefficients can be taken as high as you want. Is that the idea?
That depends on the couplings of these additional terms. That in principle, yes. I mean, GR is a particular limit of Einstein-Cartan. There is no problem with that. Well, apart maybe from this for Fermi interactions. So here it is a prediction of Einstein-Cartan which you cannot eliminate.
Okay.
Yeah.
Okay. Thank you. I see.
In string theory, the torsion would be dynamical, right? Because
as far as I understand, yeah.
If I remember correctly, the kinetic term, the field strength is the 3 form.
Mm-hmm.
That's my memory from 20 years ago.
Yes. It's dB, right? That's the field strength. B,
right. B is that's the 2 form, and the 3 form is H mu nu sigma.
Right.
Okay. Thank you very much. Yeah, I was just trying to connect it to various other things I've heard. So.
Yeah, no, that's always interesting, of course.
Yeah. I have to run, but this was a very interesting talk. Thank you.
Yeah.
So I just have a question about the scalar kinetic function there. I mean, can you interpret that as some coset of some symmetry breaking or not?
So scalar, you mean the kinetic term of the scalar field?
Yeah. Because this is it's like a nonlinear sigma model that you have there. There's some, I mean, there's some non-trivial structure in the scalar sector. So it's as if you have a manifold, there could be some symmetries that you broke, and then that's the coset, but there's nothing like, is there any interpretation like that?
Okay, here it's not different. From this point of view, it's not different from just standard Higgs inflation, from the original Higgs inflation. Or in fact, so, okay, the origin of this non-trivial kinetic term is very simple, right? That's what you get when you perform the Weyl transformation of the metric. So the theory doesn't change. You introduce new variables, but the symmetry remains there. It may be realized in different way. It's true. So I mean, the scale symmetry, for example, will become the shift symmetry when you introduce it. When you switch to a canonical scalar field, scale symmetry will become shift symmetry. But I don't think there is more than that.
Okay. Yeah. Okay.
Any other questions?
Yeah, well, let me just, related to symmetry, like the general comment is that, of course, it would be very interesting to look for some specific symmetries that would forbid all terms in this general Einstein-Cartan action, except those that we like or that we want. But that is non-trivial. So there is no way to forbid terms like R squared, for example. I don't know any. Mm-hmm. You can argue that, okay, we don't want new degrees of freedom, and therefore terms like R mu are excluded, and many other terms are excluded, but not all of them, unfortunately.
Okay.